All right, so here we have the first topic for today, that is voltage. And once again, I'll be explaining each and every concept in the key terms that are proposed by Cambridge for your physics exam. So these terms, voltage, potential difference, EMF, they are explained in different ways. And matter of fact, these are very detailed concepts. We have there are complete books, complete chapters written on these things. But here we explain uh, as or in a way that is proposed by Cambridge. Now, first of all, voltage. We said that electric current is the flow of charges. So if you have charges in a conductor and they are moving in a certain direction, that constitutes or that makes current, electric current. Now, in order to make those charges move in a certain direction, or in order to make the charges move, there must be or they must be supplied with some form of energy. So the energy that each coulomb of charge is having is called voltage. In simple words, in order to understand the voltage, that's a raw definition. Raw definition means just for the sake of understanding. So we define it as energy that each coulomb of charge has. That is called as voltage. So basically, in simple words, voltage for a charge would be the amount of energy that one coulomb of charge is having. Coulomb, once again, we studied in the previous chapter in static electricity. Coulomb is the unit of charge. Charges are measured in coulombs. Now, the exact definition is energy supplied energy supplied to a unit charge in a circuit. So this is the definition that you have to write if they ask you in the exam. So energy supplied to a unit charge in a circuit. So charges are moving in a circuit, and the amount of energy that is supplied by the battery or by the cell or by the power supply or by the DC generator to the amount of to the charge to 1 coulomb of charge, that would be called as voltage. Now, the unit of voltage is volts. So it sounds similar. It is similar, matter of fact. So the voltage is measured in the unit that is called volts, and that is represented by capital V. Right? For example, the voltage of a battery is, let's say, 10. So what do we write after 10? Right after the magnitude, we write down the unit, and the symbol of the unit is capital V. So that's the unit for voltage, volts. One of the thing is, sometimes they ask you the question, how many electrons are there in a unit charge, or number of charges, the number of electrons in unit charge. Unit charge, once again, means 1 coulomb of charge. 1 coulomb of charge. Now we can do it the reverse way. What we know is, on one electron there is a charge of 1.6 into 10 with power minus 19 coulombs. This is a charge on a single electron. Now we can do the reverse way. We can cross multiply that stuff. What we're trying to find, so one electron has that much of charge, we have to find the number of electrons in 1 coulomb. So for 1 coulomb, there would be X number of electrons. That many coulombs have 1 electron, and 1 coulomb would be having X number of electrons, which is basically a method of cross multiplication. Then you can, from here, you can cross multiply it, and that would be X equals, and I've skipped a step over here, 1 divided by 1.6 into 10 to the power minus 19. After cross multiplication, this is what we get here. And if you hit it on the calculator, what you get will be 6.25 into 10 to the power 18. Okay, thank you. So 10 to the power 18. This is the amount of charge. This is the number of electrons in 1 coulomb of charge. So you see, in 1 coulomb of charge, there are plenty of electrons. There are too many electrons in a single coulomb of charge. Now, back to the same stuff, voltage. Voltage, generally in our syllabus, with respect to the voltage, they further classify it into two types, which is, the first one is electromotive force, and the second one is potential difference. All right, it's not strictly a classification. I mean, we cannot strictly say that these are the two types of voltage. I mean, electromotive force, voltage, and EMF, all three of these are sometimes used interchangeably as well. So just for the sake of understanding, for the sake of convenience, we have generalized the term voltage. And voltage, when we say the word voltage, it can mean electromotive force, or it can mean potential difference as well. Now this one is very important. We have to differentiate between electromotive force and EMF first. This is a very detailed topic. Matter of fact, in A levels we study that in details. Over here we don't have to like dive into much of the details. We just be confined to the demands of the Cambridge. So first of all, we define it in the way that is proposed by the learning objectives, or in the learning objectives. And I'm just going to copy paste the definition of EMF and potential difference from there, because if you write down the definitions from the learning objective themselves, this is the safest way. Just to be on the safe side, write down the definitions or memorize the definitions as it is from the learning objectives. Now first of all, let us write down the definition, and then we try to explain what do we mean by that. So for electromotive force, we say the electric work done by a source in moving a unit charge around a complete circuit. So this is how we define the electromotive force in our syllabus for the physics exam. Now, what are the key terms? The key words are electric work done by a source in moving a unit charge. That's another key word. Around a complete circuit. Complete circuit is another thing that differentiates electromotive force from the potential difference. Now, let us write down the definition for um, potential difference as well. So, it is defined as work done the unit charge and passing through component, not through the complete circuit. This is how we define the potential difference. Now, what you have to understand for your for this thing, the difference between EMF and potential difference. So, for example, this is a circuit that consists of a battery and a light bulb. This cross enclosed in a circle represents a light bulb or a filament lamp. All right. So, in order to make these charges, in order to make the electrons or the charges move through the circuit. So let's say here we have a charge. In order to make this charge move through the circuit, starting from, let's say, the positive terminal of the battery, and to make it return to the same point around the complete circuit, how many joules of energy is required for that 1 coulomb of charge? That would be the EMF of that source, because that energy will be provided by the source. If there's a battery, then the battery has to provide energy to the charge in order to make it move throughout the circuit. So, for example, in order for the charge to move from here all the way to the circuit back to this point, we have to provide 10 joules of energy to that 1 coulomb of charge. Then we say that the EMF would be 10, because 1 coulomb charge needs 10 joules of energy in order to travel around the complete circuit. That would be the EMF. We'll discuss the units later, like in what unit do we measure the EMF. So, for the potential difference, so let's say here we have the same circuit. We have a circle. This is a light bulb which is being powered by a battery. Now, some of the energy was supplied by the battery to the charge. Now, your charge is at this place, right over here. And let's say it's 1 coulomb charge. I can write 1 coulomb charge. Now, your 1 coulomb charge wants to pass through the component. It wants to pass through the light bulb. As it passes through the light bulb, your electrical energy would be converted into, in this case, light energy. How much electrical energy is being converted into light energy in this case would be the potential difference. Or, in other words, that's one way of defining it. Another way is how much energy or how much work would be done on the charge so that it can pass through the component and it can reach over here. So how much energy has to be supplied, or how much work has to be done by the charge in order to pass through the component only, not through the complete circuit, through the component only. That would be the potential difference. So this is the only thing that you need to understand for this syllabus. There are plenty of further differences, not the differences, I mean this thing, it goes into further details. It takes a reference from the internal resistance of the battery as well. but this is beyond the scope for of our syllabus. All you have to memorize, all you have to understand is for electromotive force, it is the amount of work done on the charge by the source in order to make it move around the complete circuit, but potential difference is the amount of energy or the work done by a unit charge while passing through a specific component. Now, the other thing is uh, formula. Electromotive force is represented by the symbol capital V. Potential difference is also represented by the symbol V. Both of them are represented by the same symbol. Sometimes you can represent EMF by EMF, in short form potential difference by P dot D, right? But the in terms of the quantity, the symbol is capital V. Now, for the electromotive force, we generally say V equals to work done on the charge. And for the potential difference, we have pretty much the same thing, but we generally like to prefer to write as energy converted per unit charge. And then what happens? Now, symbolically, we can write it as V equals work done is generally represented by W, capital W, so W over Q. So symbolically, this is how we can write down this formula, and pretty much same formula we have for the other one, but energy is generally represented by E, E divided by Q, Q stand for charge. And it must be kept in your mind that work done and energy have the same dimensions, they have the same units. Work done is also measured in joules, energy is also measured in joules. So technically, these two formulas are just the same. Generally, EMF refers to the voltage of a source, right? EMF is voltage of a source. So the sources are generally cell, battery, power supply, generator, DC generator, and etc. And potential difference is generally the voltage across a component. So voltage across a component. For example, voltage across a light bulb, voltage across a resistor, voltage across a motor, voltage across. When we say the word motor in physics, it means generally means any moving device. It can be fan, it can be drill machine, it can be a washing machine, it can be a juicer blender. So motor in physics generally means any moving device. So that was another difference. And then we have the standard unit. Like I said, these are the other names for the voltage, so they must be having the same unit. So the SI unit is volts for both of them, which is represented by capital V. They have the same unit. Matter of fact, once again, I'm repeating, in calculations, in the numerical questions, we don't differentiate between electromotive force and potential difference. Now, it must be kept in your mind that electromotive force, although there is a word of force in this thing, in this term, electromotive force, so it must not be treated as a force because it's not actually a force. It's the amount of energy, it's the amount of work done on a unit charge. So force is measured in Newton. Many of the times students commit a mistake and they measure electromotive force in newtons because they uh, read the word force in it and they're tempted to say that if it is a force, then the unit must be newtons. But that's not the case. It's basically the amount of energy. So it must be represented in joules per energy provided by charge or to a charge. So joules per coulomb. And how do we know that? We know it from here. If we do some of the derivation, work is measured in joules, charge is measured in coulombs. So it would be joules per coulomb. So both of them can be written as joules per coulomb as well. But generally, we don't write it as joules per coulomb. We write it as volts. But in paper one, in the MCQ, they always ask you this question: what is 1 volt equal to? So 1 volt equal to 1 joule per coulomb. All right, moving on to the next thing. So for example, here we have a battery. All right, so here we have a battery. So let's say there is 1 coulomb of charge. There's 1 coulomb of charge over here, 1 coulomb charge. And in order to, this one is, by the way, the longer terminal is positive and the shorter one is negative. So in order to make this charge pass all the way from here to the other side and back to the same side, I need 2 joules of energy for that 1 coulomb of charge. I need 2 joules of energy in order to make this coulomb of charge pass through the entire circuit back to its starting point. I need 2 joules of energy. In that case, the EMF of that cell or EMF of that battery would be 2 volts. If I needed 10 joules of energy for that 1 coulomb of charge, the EMF would have been 10 volts. If I had needed 0.5 joules of energy for that 1 coulomb of charge to make it pass through the complete circuit, then the EMF would have been 0.5 joules. Now for the potential difference, we generally represent it like this. Like I said, potential difference is generally the work done by unit charge passing through the component. not in the complete circuit, only through the component. So let's say we have a light bulb over here, and all right, so here we have a light bulb, and on this side, let's assume that it was having 3.5 volts, and as it passed to the other terminal, it is now having 2 volts, as some of the energy would have been converted into some other forms. The electrical energy might have been converted into light energy, and some of the energy would have been wasted in the form of heat. As if the light bulb is being operated, it's heated up as well. So some of the energy would be wasted in form of heat. Now the coulomb of charge is deprived from some of its energy. Now, what is the difference between the potential at these two ends? Well, the difference is of 1.5 volts. So we can say that the potential difference is equals to 3.5 minus 2. It is 1.5 volts. And what do we say? We say the potential difference across the light bulb is 1.5 volts. So potential difference is always generally across a component. All right, moving on to some of these sample questions. Here we have the first one. A cell is connected to a resistor. What is the EMF of the cell equal to? Now, EMF, it is not the power. We did not define it in terms of power. Potential difference across the resistor. Nope, we did not define EMF in those words. So if we take a look at the definition, EMF was defined as the electrical work done by a source in moving a unit charge around a complete circuit. So unit of current, no, we define it as unit of charge in a circuit for each unit of charge that passes in that whole circuit. So this is the closest option. Matter of fact, the only true option that we have. The work done in a circuit for each unit of, and when they're saying work done in a circuit, that means in a complete circuit. So C is the right answer for this one. Then we have the other one. An electrical quantity is defined as the energy converted by a source in driving a unit charge around a complete circuit. What are the keywords? So the keywords here once again are the energy converted, unit charge around a complete circuit. So that the energy that is converted or required or supplied to the charge to drive it around a complete circuit is electromotive force. Across the component, if it were across the component only, it would have been potential difference. But in this case, it would be electromotive force. Here's another question that we have. 1 volt can also be written as, so if we have the formula for volt, you can write it as W over Q or E over Q. In calculations, we don't really differentiate between EMF or potential difference. So what is measured in joules? charge is measured in coulombs, so it would be joules per coulomb. And that would be option D. So D would be the right answer in this case. Alright, then we have the next one, cells in series. So if we have multiple cells, let's say in that case we have the first one. So we have three cells which are connected one after the other. The first one is of 1.5 volts, the second one is of 1.5 volts, and the third one is also 1.5 volts. Like over here. Now, whenever the cells are connected in series, the combined EMF would be the sum of individual EMFs. So what is the sum of individual EMF? 1.5 plus 1.5 plus 1.5. So the combined EMF is 4.5. Now the next thing is, why do we connect the cells in series? It is more efficient, and it is suggested that instead of making a single large cell of high EMF, we should be having small cells, small multiple cells of small EMF. For example, if we want a cell of 10 volts, all right, just for the sake of an example, we're discussing that we want a cell whose EMF is 10 volts to operate a light bulb. It would be more effective if we combine 5 small cells with EMF of 2 volts, because that would once again add up to give 10 volts. So it is cost effective, it is more efficient to manufacture small cells and then combine them in series to obtain large EMF. The next thing is cells in parallel. When the cells are combined in parallel, their combined EMF is same as of the individual EMF. For example, the individual EMF for the first cell is 1.5. For the second cell, it is again 1.5. For the third cell, it is again 1.5. So what would be the overall EMF across the point A and B? It will once again be 1.5. It doesn't add up in parallel cells. In parallel combination, it remains the same. Now the thing is, if the voltage or the EMF remains the same, then why do we need to combine cells in parallel? The answer is, we have two major advantages. The first one is the batteries, they will last longer, right? So getting more battery timing. And the other one is, if one of the cell is out of order, the circuit is still operational. The combined EMF. Yeah, exactly. Yeah, you guessed this one right at least. So this is a compound combination in which the batteries are connected in series as well as in parallel. Now let's sort out the first one, this one chain. Let's sort out this one. So we have three cells which are connected in series. So the combined EMF for the top branch would be 6. 2 to 4 and 2 more, it would be 6. Then for the second branch, we have 3 cells once again connected in series, and the combined EMF would once again be 6 volts. Then we have the last branch with 3 cells once again connected in series, and the combined EMF would once again be 6 volts. Now, after we have sorted it out, now we have 3 cells which are connected parallel to each other. The 3 of them are connected parallel to each other. They're connected across each other, and the combined EMF for the parallel circuit remains the same. So it would be 6 volts would be the overall combined EMF of this circuit. So 6 volt from here, 6 volt from here, 6 volt from here. Then we are left with 3 cells which are connected in parallel. So the combined EMF would be 6 volts. All right, then we have a situation here. Different combinations of cells or batteries. So for instance, I have a battery, a 5 volt battery over here, which is connected in series with the 3 volt battery. So 5 volt here and 3 volt battery or cell is this one. What is the combined EMF in this case? You just take the algebraic sum and that would be 8 volts. Simply add the cells. And we simply added the cells because they were having the same orientation. Positive followed by negative, and that negative was connected with positive followed by negative. Or you can say whenever opposite terminals are connected, we simply add the cells. We simply add their EMF. Now, what if we have another situation that is something like this? So what we have here is 5 volts here and 3 volts here, but the problem is this time orientation is different. Positive, then negative first and then positive. So opposite terminals are connected in front of each other. In that case, you have to subtract the EMF. So in this one, it'll be like 3 volts minus 5 volts minus 2 volts, it would be 3 volts in this case. All right, so case number 3. Now let's say we have a situation like this. So we have let's say 10 volts here. This cell is of 10 volts, this cell is of 10 volts. What is the overall EMF? Once again, we have to be careful with the orientation. The orientation is once again different. Positive followed by negative, then negative first followed by positive. So like terminals once again in front of each other. So we have to subtract these two and the answer would be 0 volts. So matter of fact, this cell, this battery or this combination won't be of any use for the circuit. Another situation. So let's say we have one cell here, then another one here, and then another one here. And these three are connected in series, means they are connected one after the other. So the first one we have is 5 volts. The second one is 2 volts. Third one is of 4 volts. Let's take a look at the orientation. So orientation is different for of them. First positive, then negative, then positive, then negative. So far the orientation is that we have to add the batteries. So in that case, the EMF would be first 5 plus 2, which would be 7. But then the third cell is having the same orientation with respect to the second one, or with respect to the combination of the first two. In that case, we have to subtract them. So we got 7 from here, then we subtract 4 from 7. It'll be 7 minus 4. That'll be 3 volts. In that case, the overall EMF would be 3 volts. Then we have another situation. So this is what we have. Let's say 4 volts here, 1 volt here, and 6 volts here. And the orientation, about the orientation, is positive followed by negative, then negative followed by positive, positive followed by negative. What if we sort out this one first? Let's try to sort out this side first. It'll be 5 4 minus 1, because they are in the opposite orientation. The like terminals are in front of each other. So 4 minus 1, in the first step it'll be 3. So we have 3 volts here, and that is being combined with 6 volts. 3 volts being now combined with 6 volt, and the orientation is the right way, which is positive followed by negative followed by positive followed by negative. And in that case we have to add the EMF, and that'll be 3 plus 6, which is 9 volts. So these are different combinations in which you can combine cells to make a battery, or in which you can combine different cells to uh, get a different value of EMF. And all of these can be useful depending on the situation, depending on the circuit that is being discussed.